Ahoy, Captain, and welcome to this episode of How to Decarbonize Your Ship, the show in which we provide guidance on regulations and decarbonization measures, in particular making business cases, of course. And this episode we're going to look into this beauty that you see lying here. This is the Toril Knutsen, and we're going to see how shore power or a shore power refit would affect this vessel, how much it costs, and of course what the benefits will be. So what we'll see in this episode on the Toril Knutsen, and we actually took this vessel because we know quite a lot about it because of our work done for Project Buoy. More on that later. What we see is of course 100% CO2 reduction when moored. However, if you consider the whole of the vessel, including sailing, it's only about 3%, maybe a bit more, depending on your assumptions on the entire yearly fuel consumption or emission production. The CAPEX conservative estimate with all things included like switchboard retrofitting etc, but located at the aft of the ship, also more on that later, is about 4 million, that's at least our estimate. And then we have a payback period of about 1 to 4 years, but of course that's very much up to debate and we will go into it very deeply because it really depends on which assumptions you take considering all the regulatory exposures. But if FuelEU, if the vessel, which we of course assume is fully FuelEU compliant, then we're looking about a FuelEU savings of up to $600,000 each year. Before we dive into the model, the Shore Power Quick Scan, and elaborate on some of the details of the case itself and what you have to consider when doing a retrofit for tankers, because they are quite complex, first a few disclaimers from our part. The tools we use are only models. I say only models, but they're pretty extensive models that we have been working on for a few years now. You can use them yourself, you can download them. The freemium models are also available. They have limited features and limited chips, but you can see everything that we do. But please mind you that they're only a model and your case or your own models will be different, of course. They are constantly evolving. We recently made an update in which we added ports, different kinds of comparisons method, IMO, net zero framework updates, etc. And so the model you see in this video can be different than the models we have on the platform or the hub itself. They're made by humans, so that could mean there are some errors in there. We're constantly not only updating and evolving, but hopefully also doing some bug fixing. But if you find any errors or mistakes that we have made, please feel free to contact the help desk. And it's all been made with publicly available data and a lot of assumptions. But that's also the primary reason why we make these models, because, well, a model is always wrong, but some models are sometimes also very useful. So that's why we've made this model for shore power retrofits in particular. So if you have any questions at all, or would like to point something out, feel free to contact our help desk in order to not only get in touch, but see how we can help you with your own modeling or business case making. Now, without further ado, let's dive into the case study details and show you more about the Toril Knutsen and how to retrofit for tankers in particular. And here we have the Toril Knutsen itself, the vessel we had a look at. It's quite a large Aframax crude oil tanker that we assume for the model operates only in Europe. So it's sailing from Rotterdam to an offshore location, presumably off the coast of Norway, to bunker some crude oils and then come back and deliver them in Rotterdam. So we had quite a few dealings in a previous project that we did for the Dutch government, Project Buoy, where we looked into the electrification of this particular vessel off the coast in the Netherlands, at Scheveningen. We also had a look at a great report from DNV and Port of Rotterdam on high voltage shore power connection for tankers, as well as this great report from Jeroen Pruin and friends called Cold Ironing, Modeling of Tankers in particular. Both of which were very helpful to benchmark our own findings and provide you with some more context on the retrofitting itself. Because context for these vessels definitely is required. retrofitting these kinds of tankers is very hard. I mean, when it comes to OPS, of course, you know what I mean. Why is it very hard? Well, there are three primary reasons what makes it not only technically challenging, but also very expensive, or just, simply undesirable from mostly a terminal operating perspective. I'll show you that later. The three reasons are, of course, the hazardous cargo environment. I mean, crude fuels, but also chemical tankers. Any tanker is basically shipping very hazardous, explosive, sensitive material. So we have to be very careful when dealing with sparks on board of these vessels. The interface location and cable handling, where you're going to connect this voltage, high voltage, on board the ship, how to direct it to the switchboard on board the ship. Those are all very technically challenging aspects. And finally, these are all leading to safety aspects we need to consider, but there's also a somewhat lack of standardization. It is described in the standard OPS standard 80005, 1 or 3 depending on high voltage or low voltage, but these are all informative and I'll show you those later. First, the first two, the hazardous cargo environment and the interface location. Well, here we see the dangerous zone plan of the Toril Knutsen itself, and everything in gray. So here everything that's grayed out means something can explode here, whether it's liquids or gas. You can see here these are all the gaseous uptake, so that's where gas can go up. Those are all the upsides and the top decks of the tanks themselves. But everywhere here these cargo holds which hold the crude oils, everything there is explosion sensitive basically. So if everything in gray is something you want to avoid, then of course only the aft part where people sleep, eat, less explosive sensitive, that's where you want to connect from an electrical perspective. But it also means that at a terminal where you want to offload your cargo, well, you're also going to have a problem there, because the terminal itself has slightly different rules when it comes to ATEX zone, or the dangerous zones. ATEX comes from, if I'm not mistaken, it's French for atmosphère explosible. So that's standard. Those are standard saying these are the kinds of measures you have to include in order to reduce the risk of explosion, especially desirable when you have high voltage connections. And terminals, onshore standards are slightly different than shore standards. So this was taken from the DNV and Port of Rotterdam report, and there you can see that the terminal has its own danger zones and how to connect with them. And in the middle of the ship, the midship, that's where typically the offloading of the cargo takes place. So there is piping, and then the fuel is pumped from the ship to shore, or vice versa when it's being taken somewhere else. And well, it's of course easy from an operational standpoint to connect there and then reroute the power on board the ship, but you also have all those dangerous fuels and liquids and gases coming in and out, so you want to avoid that particular space. But if you want to connect at the aft of the ship over here, then of course you have the issue of you need something of a jetty or a connection management system that is on the water at the terminal side, which can be expensive for the terminal owners. So what we see in practice is that the only operational since 2008 OPS connection point for tankers in California, Long Beach, though that is also connected at the aft of the vessel. And this particular report considers many different locations, but also advises in their analysis to use the aft section of the ship. So that is what we're going to assume in our analysis as well. From a ship owner perspective, that makes it a bit easier, I have to say. Then safety and standards. Like I said, there is an annex in both IEC 80.0051 and 3. So 1 is for high voltage and 3 is for low voltage connection system, that describes OPS for tankers, what to do and what not to do, or basically prescribes it. But It doesn't prescribe it in that detail. You still have a lot of leeway when it comes to designing these kinds of systems to accommodate ship-specific but also terminal-specific technical needs. And well, there is a lack of standardization, or at least that's said in all, or that's spoken of in all of the different reports, but that's mainly because this particular annex is informative, not normative. So you may still deviate from it, and a lot of, well, that creates a lot of confusion, or confusion is maybe not the right word. It leaves a lot of options open to both the ship owner and terminal side on how to handle things. So the safety aspect combined with the informative character of the standard leads to, well, people waiting before it gets normative in order for shore power connections like these to be built. So these are just, you know, the typical run-of-the-mill tanker-specific issues. And then we still have the particular issue that is dominant throughout the board when it comes to OPS projects, and that's of course the average power demand of ships. What is exactly the average power demand of ships at berth? Because that really, not just the average but also the peaks, prescribes technically how to design the system. We had a look in our updated average shore power demand guide and database, and this is one of the graphs that we made. What we did was we basically had a look at about 7,000 ships, data points in our database. So those are all the green dots, and the green dots represent the total installed auxiliary engine on board of that particular ship. So you see there's a lot of deviation, and we plotted it with respect to GT, so that is the gross tonnage of the vessel. Those are the green dots, and then the green line is the power law function that we plotted using those dots. And in fuchsia, very nice color, it's like the purple little color, those are all either real-time measured data or representative data points that we collected from various reports. And there you see, and that's the average power demand at berth. And we highlighted that little box at 30,000 GTs, which is, by the way, a lot smaller than the Toril Knutsen that we were looking into, just to show you that if you have vessels of roughly 30,000 GTs, we already see, well, almost one order of magnitude difference in average power demand. So it really depends on what kind of ship you have. Luckily, when you consider these types of tankers, crude oil carriers, etc., we know that they have more or less fixed routes, or typically, you know, we don't have a lot of these kinds of terminals in the world, so there are not a lot of places for them to go pick up and do stuff. But I mean, then again, there are so many different ships out there and instances and configurations that I continue to be amazed with every day. So we know there is a high degree of variability. For this particular vessel, we also know a lot about the average shore power demand when idling at anchorage, but also what it's doing typically during operations. And luckily, our tools allow you to work with those assumptions and input your own average power demand, and you instantly get your business case. So you can actually play around with the average power demand to see how that would impact the business case. So what we are assuming for this particular case study is that we have about 3,800 kilowatts, megawatts, 3.8 megawatts of average power. So two of its engines running at about 50%, and then several peaks per day when pumping a lot of up to 80% of engine load, up to 6 megawatts at a time. So you see that we're actually on average roughly around the average function that we described, with higher peaks from time to time in order also to accommodate pumping actions, etc., but also to scale the onshore infrastructure as such. But again, all these kinds of things that we encounter almost every day, these problems are the whole reason, of course, that we built not just the shore power quick scan, but our tools in general, where we can input all the different assumptions, make different scenarios, change the power demands, change even the ships, change fuel cost, regulatory exposure, etc., in order to get instant insights in the business case, and that means cost benefit in terms of life cycle analysis, LCA analysis. So let's have a look at that particular ship, and especially have a look at the sensitivities to different regulatory exposures and what the kilowatt hour price or megawatt hour price would have to be from a ship owner perspective in order to make this retrofit economically attractive. Okay, so blah blah blah. Now let's finally dive into the tool. We've had all the necessary stuff done, and we can move on to the fun stuff. If you go to our website and then go to case studies, then you should be able to see the business case to refit a tanker to use onshore power supply, OPS. It's also on the decarbonization, or you can simply search for it, or you can enter the URL that we have here. And then we have more blah 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 here on top, so we can scroll all the way down to go to the tool itself. You can also go to tools, Shore Power Quick Scan, and have a look. There you can actually upload several different vessels. But of course, we are going to look at the Toril Knutsen. So everything that we have discussed previously or shown up top is loaded into this particular model. And if you have a look here, you might think, hey, this actually looks good. We are in the first years maybe losing a little money. Then after IMO kicks in, and this is something I'm going to explain later, that's when we actually start saving money. So this whole business case is based on the fact that we save money by means of everything listed here: fuel reduction, maintenance consumables. We'll also have a look at it. EU ETS, we're not looking into UK ETS, works the same, but we have a Rotterdam something else route only. FuelEU penalty and IMO. So typically you have to move from left to right, and if we do that here, this is where you can include all the ship particular details. I see that it's really going well. It's a bit sluggish. Ship properties, here you might be able to change some stuff also on the main engines. These are actually also required to input, because when calculating FuelEU and IMO, we have a look at the entire yearly profile. So if you actually achieve savings of or a reduction of your greenhouse gas intensity with using shore power, you actually get benefits while sailing. So that's also a nice benefit from OPS. And here you can also check whether or not the assumptions that we make for fuel consumption while mooring or average power demand is correct. So we can also, change this. Not that I'm, let's see. So if we just change the average shore power demand, then you'll definitely or instantly see the difference on the day rate. If we change that back to 3,800, so let's see. Yeah, that's a lot better. So in this case, the more we consume, the more benefits and savings we have. And we can also set the operational and power demand, the voyage itself. That's also nice to see. So you can actually change different ports, EU ports, UK ports, other ports. That has to do with the regulatory exposure, the amount of port calls, the amount of berth dwelling time, whether or not that particular port is OPS ready. As you can see, that really impacts the total business case. And then we get an estimate on where the ship goes, which regulatory exposure it has, how much energy it consumes, in what operational profiles, and there we do all the based on those assumptions and inputs, we do all the calculations. And of course, this was the representative power demand that I discussed. So we have about 40 port calls, 60 days at berth, of which half is in Rotterdam, the other half is offshore somewhere. So that's why we keep the conventional mooring still as a 50% of the time doing mooring on auxiliary generators. So then it just runs on the auxiliary generators, not OPS. And then the other half, we have this representative energy demand at berth. So that's the power that we need to deliver while we are spending time there. Engine characteristics, this is actually quite important, but I really have to sit down with the ship owner, which I did in this particular case, but even there were some the discussions on what the exact SFC might be, when and at what percentage the engines might be running, which engines are on and off, etc. So there's still some debate there, but here you can see at least the input parameters and assumptions we have for the different engines running. You can change assumptions. You can actually change the SFC curves so that you actually get a better or a worse fuel consumption with respects to energy generation on board. We're going to keep it as it is, but just as you see here, everything can be changed with respect to the input parameters, and this is simply a check so that you can see whether or not the total calculated average power demand is correctly transferred into an average fuel consumption and energy consumption at berth. Alright, the technical specs, I'm gonna skip most of them for now. What's good to know is that for this particular case study, we assume the worst. I mean, it can always go even worse, when what's the saying? Just when you hit rock bottom, they throw you a shovel. I mean, things can always get more expensive, as we know. But in this particular case, we assume one shore power connection panel at the aft side of the ship, and then switchboard modifications required, so maybe an additional panel, updates, the switchboard cabinet itself, the let's see, the electrical, we have it here. So we actually have the onboard main switchboard where electricity comes in from shore, and this needs to be updated with breakers, additional stuff, etc. And also a transformer is required on board in order to do galvanic protection, but also maybe up or down, probably down, transforming the voltage down to the level that is required on board the ship, which is 6.6 kV. And because of the peaks we have of 6 megawatts, we actually took a little higher amount of rated power OPS equipment. So actually everything needs to be rated to, in this case, 7.6 megawatts. And we typically scale the costs of the equipment as per the rated power of the equipment itself. So we just multiply it with one particular number, which I'm going to show you later. So this all leads to the following business case. And here we have a cash flow, or basically cost benefit, so cumulative cost benefit. And we're just going to first click you through all the different assumptions so that you can see how that impacts the model. So if you don't need a retrofit, or you don't need to spend $4 million in order to get energy on board, then you can see that it's instantly beneficial, because basically we save money by using shore power. In this particular case, we decide to start in 2027 onwards, so about 6 million over time. But we're going to keep that in. We're going to maybe change the CAPEX later on to see how sensitive it is to changes. We can also do financing. That means that we can simply finance the CAPEX through a loan. So instead of CAPEX we have OPEX, but in this particular case the debt or the interest is probably a lot more than the CAPEX cost. So it doesn't seem to be very attractive. Then we also have fuel at berth. Of course, well, yeah, if we remove that part of the equation, same as electricity, yeah, that's a bit nonsensical, because we still have to pay for fuel and electricity. So let's just leave that in. Maintenance and consumables typically don't have a lot of impact on the equation, but it really depends on the assumptions of the hourly rates of the engines. So how much cost do you have in running the engines? And then of course EU ETS, FuelEU, IMO net zero. This is why OPS is becoming more attractive to ship owners, because usually this was a typical business case for a ship owner. They simply had a look at the amount of fuel you use, the electricity cost, and then, well, you get an electricity cost needed to get a positive business case. So let's start there. Let's start with just the OPEX in this case. So we have the amount of shore power days. Well, we don't want to spend more time using shore power, but you can always adjust that particular one to see how that would impact the case. CAPEX, we'll do it later. So electricity price, that's one. So there is a particular electricity price at which it becomes more or less attractive to use shore power. But here we can't find it. So let's see if in OPEX we can actually adjust it further. Here you can see we plotted the difference of fuel and electricity, and maybe if we can, yeah. So here you can see that the pivot point at which it becomes more attractive to use shore power is about $125, $150 per megawatt hour, or 15 cents per kilowatt hour, which is typically the number or the value I use also when looking at these things. So that's the cost to generate electricity on board using your auxiliary engines. But we're still losing money because, well, the retrofit, 4 million. We're not saving enough money, $38,000. Yeah, no, that's not something No, so that's not really feasible. We can reduce the depreciation, so you can see, nothing helps here. The only thing we can do is cheaper electricity, but even then, I mean, we need to have almost free electricity, and then even then, the amount of money we save is not enough. Okay, so this is, I think, a clear example. Let's see if maintenance or consumables can make the difference. No, it's just CAPEX is too high. We'll change CAPEX later, but here this is for me really the clearest example of how regulatory exposure makes a thing like OPS more attractive. Because suppose we have a standard going rate of shore power, which is roughly 24 cents, euro cents in EU, as far as we can tell right now. So we add EU ETS, okay, more attractive. We add FuelEU, yeah, that's where we get most of the benefits, and also IMO, boom. So these regulatory costs actually help us save money. There's one thing that we didn't do yet in key regulations here. What we can do is, instead of paying this particular penalty, we can also either pool or pay for the pooling itself. So you don't have to pool inside your own fleet, but pool with another ship owner that lets you pool for money. And then, of course, these costs are reduced significantly. So that's a feature we're going to add later on. But this is the very least that we can save at the moment. And we can see that in this particular case, we have about 4 million for this electricity price. So price parity in this sense, well, that really depends on the ship owner. But we have about $375 per megawatt hour, which is quite a high price. And considering that currently the fuel price is increasing, so you can see that with a higher fuel price in the coming years, it might actually be a good moment to start using shore power. I'm gonna leave that one slightly lower. If we add maintenance consumables, you can see this can, I said it has a limited impact, but it can bring payback time ahead with about a year. So that's well, I mean, 500,000 savings. That's still pretty decent. The savings themselves, as you can see in the reporting year, the further we go, the more savings we get from regulations. The other savings typically are, in our models, flat. We can include what's the word? Inflation, those kind of things, but that's really up to you to decide if you want to add that, or net present value stuff, blah blah blah. Here, you can do that here if you want to, especially CFOs like it, but. Anyway, so the end of the analysis. So here you can see that the further we go, the more money we're going to save. So that's good. It's actually in the first few years where, well, things become tricky because FuelEU, IMO, and IMO hasn't kicked in. FuelEU also after 2030, it really becomes more stringent. EU ETS, well, it's a matter of how much it is going to rise. We typically assume 7% increase on a year-on-year basis. And then it's up to the simple game of electricity price and fuel price. And of course, whether or not it's obliged. So if we have a look at the break-even price, the megawatt break-even price, and let's say all the way down to 2050, you see these bumps. Those are typically the FuelEU bumps. The more exposure we have to FuelEU, so if you change your voyage to 100% FuelEU, a lot more shore power in the EU, you're going to see more profound bumps, because then it really starts impacting what you can do. How much? Yeah, then you're just going to have to pay a lot for using onboard generated electricity. But here you can see the electricity price itself. So if we look into the future, but I know a lot of us don't, everybody cares, but I mean, looking 5 years down the line, that's pretty far away from most ship owners. But if we look really long term, then we can see that actually prices of electricity price, well, you can even look here. If all these regulations kick in and you still have a vessel sailing in between 2030 and 2040, so if you still want to be sailing in 10 years time, you're going to be looking at a price of about $500 to $600 per megawatt hour generated, considering all these particular components. So that's pretty interesting, and I can probably spend probably not days, but hours at least, talking about the intricacies of the model, etc. I'm not going to do it. I'm going to save you that hassle. just reach out using the contact us button here. Or if you want, you can have a nice generated PDF report, which is nice, like a nice little souvenir of your case study with all the different scenarios, the input stuff that you did, indexing of prices, blah blah blah. But well, you can do it all. You can do it all here. Bottom line, I think what I learned from this analysis is, apart from adding a few features to make sure that FuelEU is properly represented, it can become very interesting for ship owners, but also for ship owners who spend a lot of money on the refit, which reminds me, we still have to look at the CAPEX. So it can be feasible, but it really depends on your voyage, and if you have an EU, if you have a lot of EU regulations in your voyage, and we have a non-harmonized future where you have to pay a lot for FuelEU and IMO, then yes, definitely do it. So one more thing, if we go back to the business case, cash flow, so ooh, nice. End of analysis, we're going to go back to 20 something here. Yeah, so what would be the impact of the retrofit, the CAPEX cost? So here we have a nice little slider, you can see, so there is a profound impact of the CAPEX in this case. If we don't have CAPEX, we're a very happy panda. If we have a lot of CAPEX, the 4 million, that is, I think, it's a lot, but it really depends on the switchboard and requirement of a transformer. Switchboard, probably not. A good chance that you can still squeeze one of these in if you have spare breaker, but transformer, high likelihood of having that, requiring that on board, and of course you need the connection panel. Luckily, you can change everything here. So if you look at more info here, you can see the assumptions that we make with regards to the different equipment, installation, etc. And everything is customizable, but don't look at all the engineering costs. Look at the equipment costs and the long lead items, because, man, those are definitely the biggest piece of the pie. But yeah, the 4 million is high. I think 2 million something is more feasible, and then you can see that immediately your business case is a lot better. But this particular business case depends a lot on the combination of, like I said, high EU voyage coverage, EU regulations, EU ETS and FuelEU, but also IMO penalty kicking in or not. Because if we don't have IMO, let's see, yeah, then it's still gonna be tricky. Okay, so let's have a look at that scenario. No IMO, but we do have a higher MDO price. Okay, that helps. And then we have an electricity price of 340. Okay, this could still be something that's interesting to the average ship owner, but then again, it really depends. It really depends. All right. I think, I think we're gonna call it a day with regards to the analysis. Man, was that fun! I mean, I've had such a great time working on the model, doing the model, checking the model, working on the model again, doing the model some more. I love the model. No, it's really a passion of mine to have a look at these business cases, see what's needed for shore power retrofits. For the last 10 years, it's been a blast, and I continue to be amazed about the possibilities. And if you want to use the same models, if you want to use everything that we have at your discretion and exposure, all you gotta do is sign up to the hub and get all the tools, the support and the solutions at your fingertips for you to use. Looking forward to getting in touch. Let us know if there's anything that we can do for you. You can always contact the help desk, and until then, have a great day.